Sensornya di sini. Ini relatif dekat kalau kita dari sini. Nah ini jadi yang
Okay, we will move on to the next paper presentation. Unfortunately, this paper presentation is from myself. You can see the title here. This is the anomaly detection in raw audio using extreme learning machine. Next. Okay, yeah, we all know that anomalies is something that are not as expected. It is not something that are normal behavior. So that in sound there are something that there are some abnormal behavior or some anomalies in the sound too. And we want to try to detect those anomalies. Hopefully, by detecting those anomalies, we can identify some various activities that are not normal, such as the indication of error in those sounds, or maybe there are some malicious activities, or maybe some critical events, like if there are some gunshots, suddenly there are some gunshots, or if they're in the middle of the network, everything is very silent, and suddenly there are some glass breaking, something like that. So we want to try to detect those things. In this research, we are using the dataset from TUT Rare Sound Events 2007 dataset. I will explain to you what is the feature in this dataset later, and then after we got the dataset, then we do some feature extraction from the sound. There are some features that needs to be extracted from the sound, and then we do some normalization using the standard scaler. Then we will split the data into some of them as the training data and the other as the testing data. And then we will do the training using the algorithm that is called extreme learning machine. Then we will evaluate the result using the accuracy of the detection. Okay, these are the features from the sound dataset that was extracted. There are 7 features that was there are 7 types of feature that are extracted. One of them is MFCZ. It consists of 20 features, and then there is pitch, consists of 2 features, which is strength and frequency, and then the intensity. We take the mean and standard deviation of the intensity, and then the amplitude, the energy, power, and harmonics to noise. So we can sum up to 29 features that was extracted from the sound. And then in this research, we are using extreme learning machine. It is a type of feed-forward neural network. So, maybe some of you have already heard about neural network. It is very popular now. It is a feed-forward neural network that employs single layer or multiple layer of hidden nodes to perform the task, any classification task. It could be image, it could be sound, it could be anything else. But in this case, we are using this ALM to perform the detection in the sound. ELM also has been advocated as the solution to address the challenge of slow training speed and overfitting. So, in some research, it is claimed that ELM can cut down the training time. Because if you are training something big like video or or maybe images or sound, then the training time is very long. That's why we need some algorithm that can cut down this training time. And then it can also give a better yeah. And these are the data set that we use, the TUT Rare Sound Event 2017. It consists of 15 different acoustic sound, everyday sound like water or something else. So it is an acoustic sound from everyday life. And then this data set has been classified into 3 classes. The glass break as the anomalies. There are 3 anomalies. There are in this data set. The first one is the glass break. The second one is baby cry, and then the last one is the gunshot. And in each of these class, there are around 500 mixture. So overall, there is around 1,500 data. Then we split the data into 80% as the training and 20% as the testing. And then, can you wait a little bit? Yeah. And then we do, as you know, the neural network consists of several layers. In this case, we use 5 dense layers, dense 1 up to dense 4. Those are 5 dense layers, and then 1 dropout layers. And these are the results from our research. You can see here that the accuracy from the training and the testing is quite good. It is above, in average, it is above 90%. And the loss, the model loss here, for the training it is still good. However, for the testing, there is not much effect on the number of epoch in the model loss. And these are the confusion metrics. The confusion metric of the result, of the evaluation result. There you can see that the glass break is the best class that can be predicted using our model. The same, So, from this research, we can conclude that extreme learning machine can detect the anomalies in the data set. In this case, is TUT Rare Sound Event 2017 quite well, because the accuracy is quite high, 98% in the training and 93% in testing, in average. And the training loss is near 0, even though the epoch doesn't give quite much effect. But the training loss is still near 0, it is under 1. So we can say that it is, this method can be used well to detect the anomalies. For future works, we try to include adding in some data augmentation, so we can try to augment our original data set from TUT Rare Sound, and then try to avoid overfitting and underfitting. That's from my presentation. Is there any question? It's impossible for me to ask myself, so if there is any question, I would appreciate it. Oh, there are 3. Yes?
Yeah, okay. Do I need to introduce myself or?
Yeah, please.
Okay, so my name is PTRN2. I'm a student here at Informatics ICTS, and there are a couple of questions I want to ask. The first one is, sound has duration, right? So like, for this model, like, what is the duration sound that this machine learn, or how long is the duration of the sound that you extract the feature on and then to train the neural network? And my second question is, you propose the neural network architecture with like 5 tensor layer and 128 neuron. Like, what made you choose that particular architecture compared to any other?
Okay, so for the first question regarding the length of the data set, it's already prepared by the data set tutorial sound event. So I just used the original one that has been prepared by them. Unfortunately, I didn't do the exploratory data analysis on how long each of those and how is the maximum length and the minimum length of each of those data. We haven't done the EDA yet, we just use the original data set. And then for the second one, regarding why I use those parameters, use those layers and the neurons for the architecture of the ELM, it is based on some experiments. We do some experiment in using several layers, and then those are the best that we did, that we got the result from. Okay. Any question?
My name is Theo. I have a question that from your presentation, you are aiming to create a machinery that identify noise, right? And when I see your presentation, someone it's passed to me about a system called noise filtering, and I wonder if there are difference between your identifying noise system and noise filtering when your system try to identify noise before doing.
Okay, yeah. It is a little bit different because if noise filtering means there are, it is one type of the anomalies. It is one type of the anomalies where the data itself has some type of noise that make the result is not very good, right? You cannot detect what exactly the sound itself. And in this anomalies, sound anomalies, it is trying to detect different type of noise, not just the general noise that are usually detected. It is just from different point of view, but the text itself is kind of the same. Okay. So I believe if we use it to this algorithm, if we use it to detect some noises, it will also work. However, we haven't done that yet. We might be able to do that in the near future. Thank you. Any other question? No? No more? Okay. Thank you. That will conclude my presentation for today. Not for today because I have one more presentation later. But we will move on to the next presenter that will present a paper, an advanced draft embedding framework with node embedding to design water pipeline network. Time is yours. and the frame to define the curve and line. About the network or the pipes, I generate graph from EPANET and then actual layout and representative graph like that. This means if graph representative the pipe on the network and the node is made a junction. Actually, we use this offline. Next is about emerging sphere and actual test to emerging sphere. Yeah. And next, the first I will explain you about graph editing. Graph editing is my architecture in our system. The first we input initial graph and framework of graph embedding in a random walk and a skip graph. Input graph, enter the system, and then random walk. You will make a sequence nodes. Then make a path out from the source node to neighbor node. Maybe you can next slide. About the random walk to make a path the source node to the context node. Example, you context source node and then feed x and y is mean a context node, and we use probability as translation. And number make a path from the source node to a neighbor node. Neighbor node is a node, it means a context node. And the work that is formed depend on the field of parameter, include source node or initial node, and then walk length. The random walk process depend on the transition probability between nodes. And the next slide. Kripper use a neural network approach to obtain vector as representative of graph node. The seed graph architecture consists three layers: input layer, hidden layer, and output layer. In the input layer, we use weight metric, and the first maybe we can use identity matrix, and if we want to determine source code, we will give one score and another node 0 score. Input to the skip graph is one hot encoding vector with length equal to the numbers of nodes in the training data. The purpose of skip graph is to predict the context node which are close the current node. Then next, we use two process feed forward and back forward processing. It will train relation between the source node and the context node, resulting from the random process. And next, we use a source map function to normalize and to optimize of the training, because in softmax function we reduce prediction error, and then after we finish skip graph, next I will clustering. Before I make a clustering, I think after before in architecture. Next. No, before. In architecture, if I finish the process in skip graph, we restart node embedding, representing a node in embedding space, and I cluster in embedding space. Before I cluster, I will get an optimization number of clustering using slot analysis, and I use spectral clustering because advantage of spectral clustering, especially in graph, and I determine spectral clustering. Output of the process cluster of nodes as a vector on embedding space. Next. After clustering, I measure similarity to nodes, and then between two nodes, and then I use minimum spanning tree. I use Tosca to optimize using pipeline in network. And next. In input graph, I use AppNet to make a graph because AppNet have a capability in make a graph design. And next, it is a process input graph, node embedding, and then cluster optimization. Next, this input graph, I use 72 nodes and 88 edges as a visualization of a water pipe network. And then I focus to construction the water pipe was to optimize of the use of pipe within the network. And next, after we validation graph using AppNet, the graph we enter
the system, and we use random walk and the skip graph to put the node embedding. Next. The part of node embedding, the other of skip random walk, we use a skip graph. In the process, we use a source map function, and then the gradient utilize to update the embedding of the node two nodes, enhance the assemblability between the embeddings of source node and the context node in the vector space, and then the result of node embedding. And I use for value in dimension because I want to know the behavior of the system about the number of dimensions, and then I use 8, 16, 65, and then 100, and the result. Next. Maybe I miss one. And the next, clustering and optimization. In clustering, after we take a solid analysis to determine the number of clusters when optimal in the system, I use a 5. I use a 5 clustering. Last number of clustering next, and the result after optimize, I generate graph, and left with not embedding, and then the right without not embedding, and comparison with two graph, I get the pipe remove arm like that, and then next, the result. I want to know about the window size parameter to determine number of nodes the skip model used to predict the node context 1, 5, and 10, and then the impact of the window size, the red pipe 18 and 5 and 10, the red pipe 17. And next, the conclusion, I want to make a optimize using the length of pipe in the network using graph embedding through node embedding.
Thank you. This is Arvida for the presentation. Any question from the attendees? No question again? Then it is my turn again to ask the question. So, what is the advantage of using the node embedding in creating the pipeline?
Because I improve the method of the embedding combined with the vector clustering, and then with the full-scale algorithm. And I use not emitting in big block. I combine to make a layout network because I think before I reset I cannot find about the problem.
So is it applied to water pipeline in any cities or something?
Yeah, in my research, just water pipeline.
In Surabaya, or it's
Oh,
just
the first I just route from Epanet to Singapore.
oh,
And the next during this year maybe I use data set in the ICTS around.
oh, okay. So it is not yet implemented into a real case. Thank you, Mrs. Alvida, for the presentation. It is very interesting. Maybe by using this, we can get better pipelining mapping. Thank you. Applause for Ms. The next presentation is for the paper trajectory prediction using Kalman filter method as collision risk assessment on autonomous track. Is the presentation oh, okay, you can present now. Maximum 50 minutes.
Good afternoon, everyone. Thank you for having me. My name is Nizar Hari. Want to present our paper here. Trajectory prediction using Kalman filter method as collision risk assessment on autonomous tram. Tram is a railway vehicle that usually in middle of the town that have its own rail. But this one is an autonomous tram. So its rail is actually a mark in road that autonomously run through it. It run in the same road as other vehicle like cars, opposed than having its own rail. So why do we make the autonomous train? Well, the first one is the lack of awareness in the discipline of the road user. That the previous research found that there are a lot of incidents between trams and pedestrians. There are 7,000 cases in year 2020 and between 2020 and 2021 in Europe alone. And then this trajectory prediction system is important because we can see in autonomous tram system here, they take from sensor into the perception, in which perception gather the data, so that the data can be used to in decision making that decide whether the tram need to speed up, slow down, or even brake. And in the decision making, the trajectory decide tell whether there is an object having in front of the tram. Next. The research object, of course, the autonomous tram and road user around tram, whether it's cars, pedestrian, or other things. And the purpose of applying the Kalman filter method and using the trajectory prediction result as the risk assessment, in which the risk assessment will produce time to collision data and distance to collision that we can use to calculate the track value that we'll use to determine whether the tram will speed up or slow down or even brake if the distance to collision is very small, for example. And the next, for the trajectory prediction, we use Kalman filter and interactive multiple model that we get from the previous research by Follows about his research about multiple model Kalman filtering scheme, in which we first use Kalman filter method, which have two steps. First is the prediction step in the left, and the updated step. So the prediction step, it predict the step using the previous state, which in the state is just the coordinate of the other object like x, y, and the speed we get from the xy itself. So for example, the first minute the xy, and then we just reduce it the next. We just reduce the next coordinate by the previous one to get the speed, etc. Just gonna explain it briefly. For the next one is an interacting multiple model. We use this because previously we feel that Kalman filter alone isn't enough, so we need to use we use 3 different model that works together to make it a better prediction. So in interaction multiple model, they have a few steps like interaction step, where the prediction step of the Kalman filter usually occur in x1, x2, we use 3x because we use 3 models, and then the input mix, and then go to the filter, and then go to model probability, and which determine the value of each result, and then output mix combining. You can continue. And the first one is the input mix, which this decide how this one manage how the result of it to transition from one model to another model. So the result comes from the model 1 to 1, which is the constant velocity, and the second one is the constant acceleration, and the third one is the constant turn rate. And this part managed so that each probability model transition from one model to another. Next one, this is each model for each Kalman filter. The left one is Kalman filter constant velocity. The other one is Kalman filter constant acceleration, and Kalman filter constant turn rate. The first 2 model it's constant, while the last one here, the delta theta, it comes from theta multiplied by the current time, and theta comes from pi divided by 180 times x radians, in which x here is a hyperparameter in radians that we can change, and we choose a default of 0.1. Okay. The trajectory, the probability update step, the probability model here determine how much of impact each model contributes. So previously we can set that maybe we want the velocity higher to take result than the other, and etc. And then the next one is the combination step. So after all that filter and then updated the model probability, we combine those results and their own model probability to get the final result consisting of result from each model, each Kalman filter model multiplied by their own model probability, whether it's maybe constant velocity 80% and the rest one is 10% or etc. And the next one, this is for the risk assessment method, the risk assessment process. The first one is we calculate the horizon distance. Now, horizon we get from waypoint, in which waypoint is the point in which the tram will follow. So it's basically the route of the tram. So we calculate what is the closest point, and then we get the horizon distance, and then we check for all the detected object and predicted detected object. If the predicted trajectory crossing the horizon, then we calculate the time to collision and distance to collision, which is here. And then using those two, we calculate the threat score. If it's not crossing the horizon, then we just apply the big number to the time to collision and distance to collision. So it's basically getting ignored since it's not crossing the horizon. So then the last, after all this look, we find the biggest threat score, which is the closest to the tram at that time, and we found the time to collision and the distance to collision of the biggest threat, and then the tram will decide what they will do after getting this data, whether it slow down or just full brake Uh, this is for the UI for data that we use. Initially we use the old window, but later on we use the one that combined with the simulation. So it's on window and then it's on combined. For the testing, we are using Karma Simulator. With each test, we have 50 run of each test. It's from start to finish, so we decide a route for the trunk to go up. And we're using fire truck here as the trunk sprite. And using Town 02 from Karma Simulator. Alright, next. And the first test, we're using just Kalman filter constant velocity. With the setting test, we're using one lap is one run across the town with town 2 and 50 other vehicles that run randomly across the map and 32 pedestrians. We got the test result of 80% success, in which there's 20% cases of the tram have a collision or just touching other objects. And the cause of that failure, we found out that the detection for the object that on the rail have some malfunction or doesn't work very good. So we work on that, and then after fixing the filter, next we can after fixing the filter, we found it increased by 4% success, but we found out also that the common filter constant velocity predicted trajectory doesn't really do well, since the predicted trajectory is always straight, since it's only using speed as a resource. So on the turning road like this, the tram usually acting late at braking, so it's usually stopping in the middle of the road or just straight up hitting another one. So we use the interactive multiple model to use not only the constant velocity but also acceleration and considering the turn rate of the other object. So for the interactive multiple model, we still get 84%, but we found out also that the previous sensor that's not really good also doesn't really work good, but we see that the result of the predicted trajectory is better, since it's actually turning like the way the object want to turn. Next. So this is the not so good sensor that that we see on the left side. The white vehicle clearly on the road, but it's not detected yet, and then it detected just after it goes over again. So it's not really good. So he's still working on it. Then while the sensor is being fixed, we run a tuning on the model and the interaction. So what we tune is the transition matrix that decide the initial probability model. In the transition matrix, it's a 3x3, in which the first up 3 is the constant velocity, constant acceleration, and constant speed rate. So we basically reduce the value of the constant velocity, and we add the value of constant turn rate and constant acceleration. So we can see from the first one, we give like 98% to the constant velocity, and then we reduce it to 90% for constant velocity and 7.5% for each constant turn rate and constant acceleration. And then and then for the hyperparameter in the turn rate model, early model, we change it from 0.1 radian and to 1.5 radian to make it more sensitive to turning. And then increasing the max iteration from 100 iteration to 300 iteration. We do this because we realize that with only 100 iteration, they rarely get to the maximum length of the predicted trajectory that we want. Like normally we want 20 meters maximum, but they usually get like 10 or 15 meters. So we increase it to hopefully make the predicted trajectory longer. So from this we can see the result. We can see the result. It's got before the tuning, the predicted is the trajectory got predicted right before the turn. But after the tuning, we can see the same exact trajectory but longer and way faster even before it goes to the intersection. So that's next. Nevertheless, and the last one, after tuning that and combining the decision making, we use the new GUI pod for a new road that's now only going straight, but we pass a two intersection. So we get 92% success rate here with no correlation to other one. With 8% case of failure is the time to collation and distance to collation are not calculated in time. So it's still too late, but the predicted trajectory is on point. Pretty much on point. Next. The conclusion, the interactive multiple modal Kalman filter algorithm is considered successful. We get 92% successful result. It's pretty successful, but it still need more since 18% in result is still not enough for the penerapan. Still not. And the success of automated vehicle is the result of all the system component working effectively. So, and the suggestion is needed discrete testing method because initially we want to test it with the ground truth, but eventually the predicted result have like a lot of points x and y coordinate like hundreds, while the ground truth is only having like 30 coordinates, so it's pretty hard to combine them. And hyperparameter is still able to be tuned more again to make a better result for me. Okay. That's pretty much from me. Thank you very much for the attention.
Thank you, Mr. Nizar. Now, is there any question from the attendees in this room? Or maybe, oh yeah, there is one.
Yes, I have a question. Is the prediction time is taken to calculation in decision, final decision? And
The prediction, at the last part of the test, we haven't really take the prediction and calculate time if necessary because we only focus on making the predicted trajectory become better. So we haven't really test how long does it take for me to get the right decision. So
That's going to be the future works, right?
yeah, only the result, only the how good the predicted trajectory with the ground truth, with the actual trajectory. Thank you.
Thank you. That's all. I think enough from Mr. Nizar. Please give. Now we can move on to the next presentation, blood alcohol concentration screening at emergency room, designing a classification model using machine learning. Is the presenter Yeah. Do you want to present it yourself or you want to use the one that you already? Okay, sure. You can start the presentation. It is 15 minutes maximum, including the question. So maybe around 12 minutes is the presentation. Yeah, sure. Is there any question from the attendees in this room or maybe the online attendees? No. Then I have one question regarding the data set. How do you collect the data set? Is it from the blood or anything? And how many data sets must you collect it? Yeah, 10 years of data, that means the training time is quite exhausting. Okay, very interesting. Thank you, Ms. Niken. I thank for your presentation. Please give a round of applause for Ms. Niken. Now for the last one is my paper again. Yeah, it won't be long. Hopefully it won't be long. Yeah. My second paper is non-compliant level of motor vehicle taxpayer classification. So, next. Yeah. As we know, tax is very important for our country. This is the revenue for our national for development and all. And one of the tax is motor vehicle tax. There are a lot of motor vehicles here, motorcycle, car, and so on. And the government usually collect this tax. And motor vehicle tax is one of the regional revenue. So it is regional, not national. And some of the taxpayer they didn't pay the tax. They usually, if they didn't pay the tax, they will try to do some kind of action to avoid paying their tax, like running away, or maybe if it is in case of vehicle, maybe they create some fake plate numbers, something like that. So in this research, we are trying to classify the taxpayer compliance in motor vehicle tax. Hopefully, by doing so, we can help the government determine what type of billing strategy they can use. If they know the classification of the taxpayer. Next. Okay. For this case, we collect the data set from the government. Two of the author of this research was the government. They are working in Pajak. So they collect the data. We got around nearly 15,000 data set of the surat pajak, we call it the surat pajak, with 16 attributes. And then after we collect the data, then we encode those data because most of them are categorical data, and machine learning cannot do the classification well. If it is in categorical data, then we encode it into numerical data. Then we do some standardization. Why we do some standardization? Because some of the data are too long. That's why we need to standardize it. After those pre-processing, then we do the classification using the data split 16 to 40, 60 is the training and 40% is the testing, and then we do the cross validation with tenfold, and then we use several classifier in machine learning, which is decision tree, SVM, KNN, naive bias, logistic regression, and multi-layer perceptron. Next, these are the attributes of the data set. There are 60 attributes. You see most of them, 1 to 10 is categorical data, some of them are numerical data, and the last one, number 17, is are the class. There are three classes in this data set. The first one is SPOS, meaning that he is late by less than 30 days, 15 to 29 days, and then the second one is NPP. It means that he is late between 30 to 59 days, and the last one is NTP. It means that he paid late more than 60 days. Next, and our result is like this. This is for the accuracy, precision, recall, and F1 score. We can see here that decision tree have the best result in the accuracy, precision, recall, and F1 score. And regarding the time taken to do the training, we can see that actually KNN is the fastest one. However, from the previous accuracy, it is very low. It is around 70%. So we can exclude that. We can say that the one that are very good with 99% accuracy is decision tree, and also the time taken to do the training is only 0.002 seconds. Next, okay. So from this research, we can conclude that the taxpayer compliant classification can be carried out using several machine learning methods. In this case, we use decision tree, support vector machine, KNN, naive bias, logistic regression, and multi-layer perceptron. We use 60 versus 40% data split with tenfold cross validation. And we can conclude that the decision tree have the best result in the evaluation. That's all from me. Is there any question? No?
I want to ask.
Yes?
I want to ask about the data split. This one using the 60 to 40 data split, while the previous paper using 80 and 20. So is there any positive using the 60 and 40 testing other than the 80, 20?
Yeah, I know. Yeah. Usually, the common data split is 80-20. It is to get a better training method, so we can get a good model. However, we are trying to do a worst case of data splitting, which is 60 versus 40. However, based on our experiment, we got a good result already. With most of them is more than 90% accuracy. That's the reason why we are stopping at 60 40.
So starting at 60, not at 80.
Yes. Okay. Any other question? That's all. Then enough for my presentation. So now we can conclude our session here. But first of all, let me thanks to all of you, the presenters and also the attendees of this session. And I would like to announce several things to you. The first one is that, is it done? Yes. There should be a closing remarks in the next door, but I'm not sure if it is still in it is still running at the next door, but there will be a presenter. Please go first to the next door in room 107 because there will be a closing remarks, and then if there is no closing remark in 007 next door, then we will directly go to the photo session. It will be in the lobby of the ground floor. Okay. Finally, we come to the end of this session. But let me again thanks to all of the presenters and all of the participants of this session. Let's give the big applause for all of us. And hopefully we can meet again in the next 2 years in the next ICTS, maybe in 2025. Thank you. Thank you ya semuanya.
Kalau mereka boleh
Thank you.